My name is Buster Franken for the guys, for the people that don't know me. I'm a founder of Fruit Punch AI, and I have the very sincere honor to introduce to you the AI for Wildlife team today, who have been working on the first AI for Wildlife challenge concerning the detection of poachers on the thermal video feed of the drones of SPOTS, the strategic protection of threatened species. So SPOTS is the main partner. Just to probably Matt will go into this a little bit as well, but they are doing a lot for conservation in on the whole continent of Africa. And specifically, they're flying drones now in Pilanesberg and trying to optimize that process. And we are trying to help them with that. And but that Matt is going to go into that in much more detail. So Matthew, he's going to give part of the presentation. Then also Faiz is going to give part of the presentation about the model and the implementation and data collection. Of course, I already mentioned SPOTS. Then another partner of ours that enabled Matt to join with such a tremendous effort is Cape AI. Also important to name. They're a consultancy company very much concerned with conservation and climate in South Africa as well.
As Buster said, this is the final presentation of the AI for Wildlife first challenge. And he mentioned our project partners, SPOTS, Cape AI, and Fruit Punch AI. What I'm going to start by doing is setting the context, and that starts with the problem. And in this case, the problem is that according to the WWF, the World Wildlife Fund, wildlife crime is the largest direct threat to the future of many of the world's most threatened species. And as I think many of us know, one of these species that is often the target of wildlife crime is the rhino. And in Africa, over the last decade or so, almost 10,000 rhinos have been lost to poaching. They are hunted, killed, and their horns cut off and shipped off on various illicit trade routes. To go with the problem, we have the main partner, our project partner and key stakeholder. SPOT stands for the Strategic Protection of Threatened Species. Fighting poaching is a difficult thing. It's a complex, multifaceted problem, and SPOTS is involved on the ground here in South Africa using their technology and their expertise to fight part of that battle. And their mission is to ensure that they use their expertise and UAV, that's unmanned aerial vehicle or drone, to produce results which reduce poaching. And their vision is to bring together conservationists, governments, individuals, and business in a combined effort to end the destruction of threatened species. So you can see that this project really fits in very well with their mission and their vision, with them having brought together Cape AI and Fruit Punch AI and all the members of the team to contribute towards this conservation cause. And this is the team as it stands at this point in the challenge. We started with around 22 people, and some people have left along the way, but we've ended with Buster and Sako, of course, and then 15 team members across 3 continents. We are a mix of undergraduate students, postgraduate students, and working professionals, all of whom have given of their time as volunteers to work on this project. So it really is quite something to be a part of it. What I'll do now is tell you about the current system before we talk about how we might be able to improve it. So here we have a picture of Robbie from SPOT heroically casting the UAV into the air. And what happens from there is that the drone or UAV is piloted via remote control. It is flown up in the skies over reserves, and that trailer that you see in the background that says Air Ranger is the operation point for the project. And so footage is streamed back from the UAV to that trailer, and there's a SPOTS person sitting in the trailer watching that footage and looking out for people. And although this was taken in the day, obviously, the majority of the work using the UAV is actually done at night, which is why it's thermal imagery rather than your regular RGB color camera that is used in this context. What you can hear from what I've just described is that this is quite a manual operation at the moment. The flying of the drone is manual. the reviewing of the footage is manual. And so what we wondered, and why we were brought in, was to see if we could improve the operation through automation. And that could be improving the efficiency of reviewing the footage and taking the load off the operator to some extent, rather than having to sit for hours at a time looking at a little screen. And also to see if we could improve the efficiency of the flight paths and bringing down the drone. So our objectives in 3 main points were for the whole project, are to detect human beings on thermal camera footage, to facilitate autonomous landing of the UAV under non-ideal conditions, and also to facilitate fully autonomous flight and detection of those people based on flying route input. So the long-term goal is to bring in a predictive element looking at the direction of people and the direction of the drone and running calculations to facilitate interception of the poachers. And something that I will raise at this point is that there are various challenges implicit in achieving these objectives. And these range from getting good footage, because conditions can be really difficult out in the nature reserves of South Africa and further afield, moving the information to and from the drone, so using appropriate radio technology to reduce latency and transmit that information as quickly as possible. And also, because many of these areas are very wild and there is not good signal generally in terms of mobile or cell phone signal, it's an important facet of the project that we need to do this using edge computing devices. So it's unlike other projects where you might have a computer vision model that can run in the cloud, and so it's less of an issue how complex a model it is and how much data there is moving back and forth through the pipeline. In our case, the UAV and the trailer combination need to be able to operate independent of any sort of mobile network. So edge computing comes into play. And what I'm going to do is show you what the imagery looks like to start with. So this is not actual footage taken during an operation. Rather, it is some simulated footage that the Spots folks provided us with. So what you're about to see is the thermal camera that is used. So that is true to reality. And then you'll see a few people walking around, and those are Spots folks doing their impressions of poachers out in a reserve. So what you could see in that footage is that humans, in certain environments anyway, stand out quite clearly. They're a lot darker because they're a lot hotter than surrounding plants, and so they stand out and look like quite prominent features. However, there are complexities that don't necessarily come across in this initial bit of footage. And what I'm going to do to unpack some of those is, for the non-data scientists and non-AI practitioners on the call, is I'm going to give you a 90-second computer vision crash course so that you understand what I'm talking about later in the presentation. So the first thing is to think about what we're actually talking about when we say computer vision. And what it means really is the extraction of information from imagery. So here I have a stylized, very simple image of a smiley face, which you can see is a matrix or a grid, and you can think about each of those grid cells like the pixels on your computer screen or your phone screen. And what these are in terms of a computer's eyes, for want of a better phrase, is values. So these are numeric values, and the darker a pixel is, the higher its value, or in this case, as I put it here, it's a binary thing, so it's 0 or 1. And in reality, we would typically have 0 to 255 as those values, and the darker a pixel is, the higher its value, or vice versa, depending on how the particular image and processing pipeline has been set up. And what the computer then does is it looks for patterns in these images. And these can either be patterns that we've told it to look for, or just patterns that it looks for through other means. And once it's found patterns, it can start to identify features. And then based on those features, it can say things about the images. And this, through various complex mathematical operations, which I'm not going to go into, leads to different types of model output. So we can have classification or classification and localization, where the model simply says this picture includes a cat, or with localization, this picture includes a cat and this is where it is. And then we can have object detection or instance segmentation, which is more complex, where we're looking at particular objects within the image or instances within the image, where rather than a bounding box, as you see under object detection, you have the full shape of the instance of interest is marked out within that image. Hopefully the less technical folks among us are still following. And then, as with other machine learning approaches, we have two sort of fundamentally different categories of algorithms, and that's unsupervised learning and supervised learning. With unsupervised learning, which you see on the left, we don't tell the computer what the different types of objects are or the different types of images. We simply feed them into the computer and allow it to look for patterns. Whereas with supervised learning, as you see on the right, we've told it, we have pink circles and green triangles, and the computer then looks for the features that are tied to those different groups. And what this means in terms of computer vision, or how it relates to computer vision, is that with unsupervised learning, we simply feed images into the model, and we do that without telling the model what to look for. Whereas with supervised learning, if we were doing object detection, we would include bounding boxes, such as you see on the right, and those would have labels. So we are telling the model or the computer, there are two zebras in this frame, this is what they look like. And if we go back to this is now a different example. If we go back to an example of our imagery from spots, we see something like this. So over here, we have a representation of one of the major challenges, which is that those animals up in the top left corner look very similar to that sun-warmed rock down in the bottom left corner. And so we start to see that it's difficult to tell animals or mammals anyway, and rocks apart. And the same would hold true for humans, being mammals and being warm-blooded. We also had the complexity of taking data from the Spots archive, which has been shot over several years and on different cameras. And so this meant that the resolution of the images were different, and some of them had borders while others did not. And that represents complexity because we need to be able to feed the model consistent images in terms of resolution as we go. And then finally, the data set is what we in machine learning and deep learning language refer to as sparse, which means that there's not much footage of people. And if you're trying to train a model to look for people, that's a real challenge. And it's also a very unusual data set. So there are quite a few projects out there that one can read about online where folks have used drones and are therefore getting that bird's eye view footage. And there are also a fair number of projects where people are using thermal cameras and therefore getting this grayscale temperature correlated imagery. But there are very, very few projects out there that combine the two. And this is an issue because we as data scientists and AI practitioners like to be, I'm not going to say lazy, I'm going to say efficient. And what I mean by that is that where possible, we will leverage the work of others. So we might try and find a pre-trained model. If somebody else has worked on a similar problem, and they've already trained a model, they've built and trained a model that could also be used to good effect in our case, then we might try and use that, in which case we would simply take the model from their pipeline, or we might try and find a labeled data set so that we could do take a supervised approach without having to go through the time-consuming work of labeling a large number of frames. So we couldn't find either a pre-trained model or a labeled data set that seemed applicable to our problem. So we decided to try some unsupervised approaches. Remember from before, those of you for whom this is new information, these are approaches where we don't label the data before it goes into the model. And we tried this in a couple of ways, one of which was anomaly detection. So we used autoencoders and variational autoencoders for the technically inclined among you. And what these do is they look for features that essentially are prominent, and they learn the prominent features in the images. So what we have here on the left, the frame labeled in is the input that goes into the model, and the frame labeled out is the model's output. So the reconstruction of the model, of the image based on the features that the model has learned are present. And you can see that there's a fair match. There's a consistency in the pattern that's there, but the subtlety, the nuance in the left-hand image is lost in the right-hand image. And given what I've told you about how and shown you about the small people in the frames and how relatively subtle they are as features, you can understand why that might be a problem. And then we also tried an unsupervised object detection approach, the SPARE model. Again, the technically inclined among you can Google that. And this shows again input and output. Once again, the large prominent features are being picked up by the model, but the smaller features, the nuance in the image, much less so. So this left us scratching our heads because the unsupervised approach hadn't worked. And so we realized what we were going to have to do was move in the direction of data annotation. We were going to have to take on some supervised learning approaches, and this meant needing to label the data. So we used this tool called CVAT, which is very handy for those of you who might be working on your own computer vision projects. If you need to do your labeling yourself, this is a good tool to use. And so here we have an image from one of our videos. You can see the people in the image there, those dark human shapes, and they now have little pink bounding boxes around them. So we can now say to the model, here's an image, there are 5 people in it, and this is where they are. To get to that point, however, we had to deal with some of that complexity that I talked about earlier. So we now had a Google Drive folder with our various videos in a couple of different file formats. We took those and cropped them down where there were borders that were problematic, but they were, for some reason, in many cases, that meant that CVAT couldn't read them. So we had to do a file conversion. And for those who might need to work through a similar process themselves, the tool that we used there was FFmpeg, which is very handy. We then also, as I said earlier, we had this sparse data set with not a lot of people in it. And so we needed to trim that down and make sure that we had relevant frames. And so we needed to take time slices of the videos. And again, we used FFmpeg, and the footage was now ready to go into CVAT, where it was converted to individual frames and exported as a coco.zip folder, which is what we required for the model we chose, which I'll get to in a moment. And what we then discovered was in some cases, we actually needed to crop after the fact. And so we developed a script in Python that would do that, and then also split the model into the data, into training, validation, and test data sets. And then we got the simulated data, which came in a different format as well. But luckily, we had this pipeline set up, and so we could feed the footage in and still end up with our labeled data that was ready to go into the model. And so just to show you what that looks like, once the footage has been labeled, we see something like this. All right, so we now have people moving around. We're seeing frame by frame, and those boxes are moving frame by frame. And we have the people are clearly identifiable. Something that's interesting to note there is how much of a role, or how much interference vegetation can play. So I'm going to play the video again and have a look at the person who's sort of most central in the frame. And you'll note that the person and the bounding box drop away when that person steps behind a tree there. And then they pop out again and the bounding box is back. So this gives an indication of how difficult it can be to spot people as they're moving through this environment. And so these models might be able to really help in that regard. And so moving on to the model that we chose, this is something that will be relevant and of interest to the data scientists and AI practitioners among you. For those of you who are less technically inclined, please bear with me. So we ended up using an object detection model from Detector 2, which was developed by the Facebook AI research group. And this is a PyTorch-based RCNN. And something that's really useful about this particular model in the context that we're looking to use it is that it provides you detection confidence. So it will say, we detected a person. The model says, I detected a person, and this is how sure I am that it is a person. And this is handy because it goes with a function where one can set the threshold of confidence, which means that if the folks at Spots think the model is being too sensitive and is identifying rocks or animals that it thinks are people, they can change that threshold and optimize the model output for their particular situation. And then we also are looking to assess model performance by calculating the intersection over union. And I think for even the less technically inclined, this is a relatively intuitive thing. It is a measure of so you have the ground truth bounding box, which is what the labelers have put in. And then you have the model generated bounding box, which has a prediction with it, or it is a prediction, and it has that confidence with it. And then to go with that, we can see how much they overlap. So for example, that top right example, there's your ground truth bounding box in pinky color, and then the greenish color is the model prediction, and it would have a very high IOU value, whereas moving down the train, there's less of an overlap in the next one, so it might be 0.5, and then very little overlap where you have the model has identified something that is not a human, and so the IOU would be somewhere, well, it would be 0 in that case. And based on these, we can determine true positives, false positives, and false negatives, and use those to calculate precision and recall. The data scientists among us will know what those are. I'm not going to go into details other than to say that these give us an indication of how well the model is performing. So we can look to optimize these parameters in various ways to then go to spots and say, this is how well the model is performing, and we can tweak parameters to improve this aspect of it or that aspect of it. And in terms of actual model output, it looks something like this. So on the left-hand side, it's a very small bounding box, but I assure you it is around a person. I labeled that frame myself, so I know. And then on the right-hand side, you can actually see the person in the road, and the model has detected what it thinks are 3 people on either side, 2 to the right and 1 to the left of the road. And so this shows where you would have a very high IOU on the left and a 0 IOU on the right. And that is where we're at the moment. So the next steps for our sub-team, just to wrap things up on this challenge, are to complete training and model performance assessment, to finalize the handover files and documentations for the next challenge team. And then the things that we suggest the next challenge team should do are to get new data, and that would include RGB, so daytime footage and thermal footage, to do a daytime and nighttime model, then label that new data, integrate the labeled data from FH Aachen University of Applied Sciences, who did a similar project but didn't follow through to the end of it, and have very kindly shared the data with FruitPunch AI, to then optimize the thermal model for nighttime operations, train and optimize the RGB model, and then write the code to stream the video frame by frame, which is the step of the pipeline that we have not engaged with yet. And with that, I will hand over to Faiz to take on the implementation team section.
Sure. Hi, how is everyone? Okay, so we work part of a separate sub-team, but integrated with the overall project called the implementation team. The objective was to eventually take the model and all the hard work, data labeling, data structuring, model building, and evaluation work, and integrate it into an edge device that could then be integrated in the UAV. So kind of while the model and data teams were doing their hard work, we were developing, I guess, a framework to operate with, as well as considerations for all the inputs, outputs, and integration factors. So this is our functional overview of what the final product should look like. A micro or single board computer of some type, represented here by the Jetson Nano, which was our first choice to start with. The thermal imaging camera, a radio mechanism, radio board. Turns out many of these are pre-integrated pretty well, and the flight controller. So with all of this going on, there's several considerations to make an actual implementation, both from power consumption, as this will be in the air, so power, battery usage for lifetime, as well as making sure the inference from the thermal image camera is working properly in both the sense of the metrics that Matt just went over, as well as time of operation. And certainly, I think the flight controller doesn't interrupt or alter anything with the flight controlling aspect. So we kind of outlined our approach early on in this project, looking at different single board computer options out there. Just briefly to go through 4 of these. The NVIDIA Jetson Nano is actually quite powerful by itself, just for the inference from a input from a thermal camera. I think it's very capable. There is a step above that, and actually several steps above that in the NVIDIA Jetson family. And you can see here, if you look at the last 2 columns, last 2 rows, power will increase, but you can achieve a significant amount of processing speed and power. So that's something to be of consideration for the next phase of this project. There's also ways to, quote unquote, accelerate smaller single board computers. So we recently started looking at this option, the Raspberry Pi, with an add-on, quote unquote, stick, a USB stick that accelerates processing power and speed. And out of the box, there's also smaller ones that are designed for maybe simpler operations or just inference, simple inference. So going back to the beginning of this project, we chose option A, which is kind of in the middle of the range of what is out there and a good platform to start with. Okay, some of the components that we considered, obviously the compute hardware, not just a single board computer, not just the Nano, but also the battery and power usage of that, as well as mechanical packaging of that for thermal considerations. In that block diagram, we have a few peripherals that we considered. The gimbal, basically the movable camera, the thermal camera itself, the radio, which now it sounds like HearLink is the type of radio series to be pursued, and the flight controller, which you can add several aspects to. We'll start with the thermal camera, but there's interest from Spots on adding additional interfaces to that as well, such as LiDAR and the daytime camera. So that's more hardware. There's a lot going on in the software as we learned through this project. The Jetson Nano has a base environment called Jetpack that comes with a lot of pre-installed computer vision packages. Torch Vision R2 that the modeling team ended up going down that path. There's also TensorFlow. And kind of the interface between Torch and the Jetson Nano is a package called Torch TRT. Detector on2 is another custom module. Onyx is a model conversion platform, and TensorRT itself. So TensorRT the RT stands for real time. It's the NVIDIA series native real-time tensor computational package, which is made for speed and efficiency, as well as Python scripts that came as the output of the modeling team's work. The point there is there's a lot going on in software, and we went through the setup, installation, configuration of this software environment successfully on the Jetson Nano. So the kind of ecosystem or environment that we headed down and have been working with for the last approximately 4 weeks of this project, with a Detector on2, PyTorch, TensorRT packages, as well as I think Matt touched on it, a lot of the pre-labeled images and pre-labeled image definition comes from an open source project called COCO, Common Objects in Context, which is very useful for a lot of things regarding computer vision. Okay, so after installation of the Detector on2 model from the modeling team and some sample test images, individual images, we were successfully able to perform the inference function at the edge on the Nano. So this is a short video. I'll kind of speak while this goes. On the top screen, you see that big green block. That's one inference running on one image. And there it stops and starts again. That's a second image. Okay, there it stops. This is a third image. So each inference on a single image currently takes about 8 seconds. So there's considerable room for improvement, and that's what we've been working on for the last 2 weeks. We're still working on that, but function is there. Each one of these blocks represents a what would be a video frame in a live feed. So I think this, as shown, is 1 inference per 8 seconds. I think the objective is to get to sub 1 second inference. The video stream may operate up to 30 frames per second. So this is the primary next step. The output. Okay, so the output of this inference fast forward a little bit here. If you look on the bottom screen now, that last output, maybe if you can, it's a series of numbers, which represents the number of humans detected in that string of images. So when running on the edge, the data visualizations are not necessary. We just want a output of the number of human detected per frame. So that's also successfully working on the Nano. Sorry. Okay, so the overall workflow is something like this. From the modeling team training a model, we export the model in some format. Currently, we're still working in Detector 2, but there's other more efficient conversion mechanisms. Generate a tensor RT engine on the Jetson Nano, which will essentially make it more efficient, run the inference, and then iterate to improve performance. And I think we've gone through 1 full loop of this at this point in time. As mentioned, this is just helpful information to move forward to phase 2, what's necessary to get going. Pre-configuration of the Jetson, more or less to make it lightweight, remove some of the extra utilities, minimize the GUI, just really set it up for inference tasks, install the packages, confirm the functionality of the Detector 2 model, and then convert to a more efficient format, and then be ready to deploy with quality and speed on a more efficient operation. That last step is not available yet. So that's kind of where we leave our work in this phase 1 is we have the function, we need to drive to a more efficient operational standpoint. Okay, yep, and I think we have all this information for a phase 1 handover. Our phase 2 proposal for next step, I think I've said this many times, but more or less drive the efficient operation. That's both from, I think, a software development, as we add features based on Spot's recommendations, as well as the modeling team's work to improve the model, as well as operating in the hardware, and develop, I think, formal constraints based on what we've considered for testing and integration. I think we need to formalize a test plan once we actually start putting all the pieces together, and add some additional features. I think the last ones here are angular and distance detection are 2 valuable features to Spot. So somehow that can be built in algorithmically. The mechanical thermal buildup is a work in progress, but that's something to consider for phase 2. I think that's realistic and deploy. That's my last slide, and I think team effort from our side, and we just over the last few weeks started working with the data and modeling team, so we hope to continue that in phase 2.
I'm gonna round up this session here. If there's any burning questions, you can always email us, of course, and we'll make sure that they will be answered. But for this meeting, we're gonna round up. So what I want to say first is just a big thank you to, well, the entire team, of course, to the efforts of Spots in assisting a stakeholder, and now here also to Matt and Faiz for giving this wonderful presentation. So this is the first challenge in the AI for Wildlife project. So of course, we are not yet at the point of a fully autonomous drone that can be thrown into the air and go and detect poachers and ping the rangers where they should intercept them. So we're going to do many more challenges after this. And we had a discussion today with Robbie about when we can do the next data collection. The goal of the next challenge here is to use more data, even that's going to be collected, to improve on this model, look for other models, and try and get the inference time on per frame, the processing time per frame on this model down, and then also include daytime footage that's going to be collected to detect poachers on there, because the poachers have moved their activities to not only during the night because of the successful flights of the spots team. They're now also trying to poach during the day, and for that there is also going to be a challenge in daytime detection of poachers, and then also in doing a census of the animals in the park. So that's another one. And the second challenge in this is going to start at the end of July. This is going to give us a little bit of time to collect the data, to get new people on board that want to join in on this challenge as well. And of course, this challenge is open to everyone that has worked on it so far. But we're going to start the next challenge on the 31st of July. Now you can register if you want to join in for the next challenge. Of course, if you're part of the team that's currently on this challenge, then just send me a message on the Slack and I'll ask you there as well. But if you're new here, then you can register through the link that I just sent in the chat here. And of course, we'll also announce this on the LinkedIn and all that stuff. And that's it for this presentation for this evening. Yeah, it's I have nothing more to add, just that since we started on thinking about doing this project when I was in South Africa, brainstorming with Robbie, who I see is smiling here. He didn't really get a word in, but I can see that he's happy. It's just so amazing to see that we're here now, and slowly but surely creeping towards making a solution that's going to be used in the wildlife reserves in South Africa. That's just really amazing, just goosebumps. So thank you all so much, and let's continue this project. And yeah, let's
Buster, just before you sign off, I think I can speak on behalf of the team when I say thanks very much to you and Sako and Luke and Khawla and the rest of the Fruit Punch AI team for facilitating our progress and for providing us with an opportunity to work on this fantastic project. So thanks very much. And as you said, I don't know if we clap, but I think, thanks to Fruit Punch AI.
Thank you so much, Matt. All right. Hey guys, there's only one thing left to say, and that's have a very fruitful evening.